So, then welcome to, this is the second lecture in the introduction to the Lattice-Boltzmann method in winter 24-25. And today we talk about the equilibrium function. So I hope that everybody either attended or remembered or watched our lecture on the ether theorem that we had last time, because this is something that we now use to get to what we call the equilibrium. Yeah, so we have to recall the theory on the ether theorem. So we said that ether, capital ether, and you will usually find people saying this is an H, and we actually don't know whether it is an H, because when Boltzmann, we don't have any recordings of Boltzmann saying, we only have his written statement, and there he puts this letter, but we have reason to believe that he wanted to say this is an ether, because it's something related to energy and not something that you describe with an H. So he defined this function that you integrate over the entire space and the entire velocity space. So it's f times the logarithm of f. And so the point of this function is that, or this functional is that you can show, as we did in the last lecture, that if you take the derivative of this, it is with time, this is smaller or equal to 0. So this thing will only change in a certain direction in time. And the interesting, so why coming up with f times logarithm of f? The interesting thing with this here is that there is a quantity in nature that you can derive from nature that only changes in a certain direction. So this is breaking the symmetry between future and past. Yeah? Otherwise, if you just follow Newton's laws, you can always invert all momenta and you will run into the past. Yeah? So this here is this thing that shows that time has a direction. So, and then this, then the reason, I don't know whether Boltzmann actually wanted to show that time has a direction. I mean, this is probably the more fundamental thing about the most fundamental thing about it, but the other thing that we actually wanted to get out of this is the question, where does it actually stop? So where is it going to? Yeah, we know it's going one way, and it will obviously stop when it does no longer change. So if eta did if d ether by dt is 0, then nothing changes anymore. Yeah? And this is the equilibrium. So this is a state, or you could say, do we know that nothing changes anymore? Well, we know that if we are there, we don't get out of it anymore. Yeah? Okay, so how does this equilibrium look like? We know that d ether by dt is, as we derived in the last lecture, we have a kernel, a collision kernel B, where we have the size of the particles and things would be inside this. And then there are the distribution functions after collision, which we indicate by this dash. So of two colliding particles, particle 1 and particle 2, minus, so this is the gain term, yeah, this is gain, minus the loss term. This is where we have the pre-collision state, so this is the loss term. And this into logarithm of f1, f2 minus the logarithm f1 dash f2 dash, and then, okay, then all of this integrated over all velocities 1, all velocities 2, all directions, so the direction play a role in the collision kernel, yeah, and all space. So this is an integral over 3, 6, 9, 12 dimensions, yeah? Okay, and now as a reminder of last time, this thing here, this thing here, including this bracket, this is smaller or equal to 0 because of the because the logarithm is monotonic, yeah, which means that whenever this here on the left is positive, the thing on the right is negative, and vice versa, so that the product of the two will always be negative or can be 0. So now the question is, when is this thing 0? dh d by dt is equal to 0 only if for all, okay, I mean for all, because for all velocities so velocities before and velocities after, so when for all velocities this f1 dash f2 dash minus f1 f2 is equal to 0. So this is the only possibility that this thing can be 0, yeah, because you know each of them, so, or let's say in every place here, because they are point-wise always either 0 or negative, yeah, when you sum them up and they are still 0, then it means they must be point-wise 0 everywhere, right? And therefore it has to hold that for all configurations of this velocities, they all together has always to be 0. So this thing here always has to be 0. And this can of course be rewritten in equation 2.1. So we have here products of two distribution functions, and what we do is we take the logarithm of of both of them. So the logarithm of f1, okay, I'll briefly write this thing like this, yeah, just to make sure it's clear what we are doing. So we put this on the other side, yeah, and then the logarithm, we take the logarithms of both sides, and because we have a product, we have the sum of these logarithms, we have them on both sides. Logarithm, so here this is before the collision on the left side and plus after collision on the right side. Okay, so far so good. Now comes Boltzmann in 1872. Now Boltzmann proved how this looks like, so he didn't find how this looks like, but he proved that it actually does. Maxwell has already conjectured how it would look like, and Boltzmann proved it. that the equilibrium is of form Maxwell conjectured and Boltzmann proved that the ln of the logarithm of the equilibrium distribution function can be written as a constant, as a parameter a plus vector b into velocity xi plus c into the square of the velocity. So xi times xi, so microscopic velocities. Now let's take the left-hand side and the right-hand side of this this equation 2.1. Yeah, so left-hand side, left-hand side 2.1. So this is okay. I've written it here a little bit different, so I have to adjust. ln f2. So this would be, so we plug this into equation 2.1, and then what we obviously get, we get the same parameter a plus b times xi, now it's without dash, sorry, dash 1, xi 1 and xi 2 plus c, and here we have xi 1 times xi 1 plus xi 2 times xi 2, so these are scalar products, of course. And then we have the right-hand side of 2.1. Yeah, looks, of course, very similar. Now I'm apparently running out of space. So here we have the ln of f1 dash plus ln f2 dash plus 2a plus b, and everything here, of course, just the same with this dash. Plus, okay, missing the c, xi1 dash scalar product with itself, xi1 dash plus xi2 dash xi2 dash. Okay, so far so simple, yeah? Now what we'll now discover is that we can identify this here basically as the mass, this here as the momentum, and this here as the energy. And there's something else, of course, important, because these are different parts in a polynomial, right? So they need to be, so each of them has to be equal individually. So these two things have to be equal, these two things need to be equal, and these two things need to be equal, yeah? So the meaning that, and I mean, one is describing the state before collision and one is describing the state after collision, and I guess it would make sense to everybody, yeah, that mass does not change in the collision, momentum does not change in the collision, and energy does not change in the collision. We need a new page. So now we've written down the logarithm of the equilibrium function, which means the equilibrium function can now be written like this. We have e by the power of a. I've just taken this out a little. And then we have e by the power of b, scalar product with xi plus c, xi, nothing important here, xi times xi, yeah? I'm not standing in front of this, or you can see, okay. Okay, so somehow of this form will be the somehow of this form will be the equilibrium function. Yeah, so we see that this can be seen as a shifted Gaussian. Yeah, where we have not identified whether C is positive or negative. Yeah, so I mean, you could say this seems to go into infinity and would look strange, but you can imagine that if this C, which we've just not specified, if this would be negative, then we'll get a Gaussian function in 3 dimensions. Yeah? Okay. So let me see. So this is basically yeah, so the equilibrium has to look like this, and more or less what now we have to do is doing measurements. I mean, seeing what is the energy in it, what is the momentum in it, and what is the mass, and then we can identify these A, B, and C. Yeah, so they will of course depend on the actual state of the matter, and the only thing that will be obvious for the reason that it cannot go to infinity at the edges will be that C is negative, but we don't know about the others yet. Okay, but we'll leave this to the practitioners to identify this with experiments, and now we are actually more interested in what we are going to do with it, right? When we want to solve the Boltzmann equation. And here we come to the idea of single relaxation time. Okay, so this is an idea that comes from Bagnagar, Cross, and Krug. So there's I'm always a little bit confused who was I think the Bagnagar is of course Indian. I think Cross was an American and Krug is a South African, I believe, or it's the other way around, but it was a international, very international group, obviously, in 1954, proposed a method to solve the collision integral, a simple method to solve the collision integral. So, I mean, first of all, you have to notice that solving the collision integral in general is not so easy. Yeah, so you see, you have to integrate the phi. Yeah, we have to integrate, I've forgotten now, over 9 dimensions or so, yeah. And you have to know the structure of the molecules and so on, and it is not immediately clear how you would do this, right? Now they had the idea that we may not know So this is supposed to be a light bulb. So this is their idea. So the thing that we know, according to the ESA theorem, that the distribution is going towards the equilibrium. And the equilibrium so the equilibrium is something that we know. Yeah? So Boltzmann, Maxwell already had the idea, so he looked at what it should look like, and so he had an intuition, and Boltzmann proved that that would be the correct one. So we know where it's going. We usually know the state, or we assume we know the state that we are beginning with. And now what we can do is we can simply ask the question, so how far from here to the equilibrium do we actually go? Now, there is a problem with this, because we are in high dimensional space. Yeah? So, when for example, I want to go to you, yeah? So then what we could do is we could simply say in a certain time, I move so and so far, so I go, for example, 20% or 80%, towards you, and this would mean I end up somewhere here, because we could assume I go in a straight line. Now, the thing with the straight line is the really difficult part, because we have no reason to assume that we go in a straight line. Yeah? But what Bagnaga, Cross, and Krug did is that they just assume we go in a straight line. So in this very high dimensional space, just a line, so and then the entire thing becomes one-dimensional. So they said, we are considering a so-called rate model. So we have a certain rate is something that so we have a certain number of collisions in a certain time, that is destroying, if you will, non-equilibrium. So they have a rate model saying that the collision operator df by dt only to collision, not to streaming, could be described as the equilibrium minus the pre-collision state divided by a time scale tau. And this is basically the way you can solve this integral if you know the tau. The tau is the relaxation time. And this is related to the mean free time. Between collisions. And the relationship is so simple that we usually say, so this is the mean free time. Yeah? So basically we can say this is the mean free time between collisions. So then the post-collision distribution function for t plus at a later time delta t could be derived from this integral f of t from t to t plus delta t f equilibrium minus f tau d tau. Yeah? So this is our simple integral to go to the post-collision state. And this collision operator, of course, as we can assume, has some conservation laws which are pretty simple. And if you think, so remember we are going on one line, yeah? We are restricting ourselves to one line, and remember there is conservation of mass, momentum, and energy. So what we know is that the equilibrium distribution has the same mass, momentum, and energy as the incoming distribution. Yeah? So and now, while we are on this one line, we observe, maybe we can prove this. Okay, and right now I cannot prove it on the spot, yeah? But what we observe is that all points in between, if this point has the same, so if the two endpoints on this line have the same mass, momentum, and energy, then all the points in between also have the same. And also extrapolation of this would also have the same, yeah? So this means this collision operator has this conservation law of mass, so which we identify in this way. If we integrate this over the entire velocity space, Feq minus F divided by tau, and we integrate this over the entire velocity space, then we end up at 0. So because this is not, this is not we are not integrating over the distribution, but we are integrating over the change in distribution, right? When the change in distribution, if there's no, so if this is 0, if the change of the distribution produces no mass, then mass is obviously conserved, yeah? So, and then the same thing is with momentum. So we get momentum out of this by using moments. Moments we get with a kernel, so we have Feq minus F divided by tau, and we have to multiply this with xi, and we integrate this over xi. Now, because the xi is a vector, this integral itself is a vector, and if you like, you can write over the 0 an arrow to indicate that this is actually 3 conditions. Yeah, so it's 0 for all the components of this vector, and then energy is a scalar quantity again. Energy, we get energy Feq, F divided by tau, by integrating here over xi dot xi. So energy velocity square, microscopic velocity square, and this is also 0. And these things here are the moments, or the conserved moments, but in particular, moments of the BGK operator. The BGK is Bagnaga cross-Krug, yeah, so this is how the thing is called. I personally don't like it when things are called after people. They should always be called after what they are doing, yeah, like here we may call this thing also single relaxation time operator, but it's commonly used as BGK. So we have to talk about moments. The moments will be our absolutely favorite topic throughout this lecture, and hopefully for the rest of your life. The moments of truth. So, because we are in an institute for civil engineering, they like to talk about the moment, where they always mean the they speak in German and they actually mean talk, and not moment of inertia or something like this. Yeah, this is because this is the most used moment. But what actually is a moment? A moment is always an observable macroscopic quantity that you get out of an integral over a field. Yeah. So basically, this is what we mean with a moment. Yeah. And so here in this, so for example, the moment of inertia is when you integrate over the space of a body. Yeah, so it's a moment in spatial space, whereas these here are moments in velocity space. Yeah, you can also have moments in time. So this sounds strange, but a moment in time would be an integral over a distribution in time. Yeah. So what we call moment is a thing that is just integral. So moments are integral properties. So that's the outcome of the integral of a distribution. And this is very important in kinetic theory because it does the transformation for us from the atomistic world. Yeah, now we have a probability that there is an atom to the continuous world. Because now we have something that Newton would have understood. And remember, Newton did not believe or think that there would be atoms or something like this. Yeah? So this is a modern interpretation. So we get something out that Newton would be familiar with. Yeah, you get the mass of an object, the momentum of an object, the energy of an object. Yeah. So, and now we have to dive into the mathematics. Okay? I warned you that this is potentially not the easiest lecture in your life. Definition. So let's get into the stuff. Let me see. Let F. Now we use a capital F. And sorry for the nomenclature with this Greek symbols. Capital F of capital Xi, vector capital Xi. We'll come to what this is. B, we let this be the bidirectional Laplace transform. Of f of Xi, vector small Xi. So Laplace transform. Are you familiar with Laplace transform? Yeah? Okay, very good. Then you know you have a field, now distribution f, and this is a function in Xi. Yeah? So now we go to frequency space, and the frequency of this Xi, so the microscopic velocity we call capital Xi. So this is the velocity frequency, if you will. And it is not really important that we use the Laplace transform. So usually when I started this, I would always say we use the Fourier transform, just we prefer not to deal with complex numbers. So you know in the Laplace transform, we know that these frequencies are complex numbers, though the imaginary part is, so to speak, already inserted in this. Yeah? And bidirectional, because usually the Laplace transform is only from 0 to infinity, and now we go from minus infinity to infinity. And then there is another caveat on this, namely, we use, unfortunately, a different convention, a different sign convention to the usual Laplace transform. Yeah? So this is because we want to get, the reason is we want to get positive energies. Yeah? So this is a little bit annoying. It's very annoying because we often get this wrong. So we say this is a plus sign. So this is opposite to the usual convention. So you know when there is a Laplace transform, there is then there is an inverse Laplace transform, and the inverse Laplace transform has the opposite sign in the exponent, right? So what we actually do is we do the opposite Laplace transform, interpreting the actual velocities as frequencies, and do the opposite, the Laplace backward transform now as the forward transform. Okay, so far the annoyance with what unfortunately is common here. I mean, it's already started with Boltzmann's definition of the Isar theory of Isar, that what he got was the negative entropy. Yeah, so he's defined something, and this stuff was negative. And now for the last 200 years, mathematicians and physicists argue whether entropy is always increasing or always decreasing, because I mean you define a quantity where you can just switch the sign. Yeah, and this just is unfortunate that people now tend to have difficulties understanding each other due to the fact that they, in the beginning, defined things in a different way. Yeah, this is like one guy drives on the left of the road and the other guy drives on the right of the road, right? So this is just the way it is. What did I wanted to? Yeah, I wanted to actually write the function. So f of xi is the integral from minus infinity to infinity. So this is bidirectional Laplace transform of over xi vector is e. So as I said, inverse Laplace transform. So there is a plus sign here. Yeah. So the velocity times the frequency velocity. This integrated over xi. So this is the Laplace transform with the conditions that I just mentioned, with complex velocity, frequency. So this capital Xi will write like this. So its first component is Xi. The second component is upsilon. I'm not sure that this resembles a real upsilon, but I always write it this, and this is supposed to be a capital zeta. Yeah, as with Isar is undistinguishable to some Roman letters, of course. Okay, now this f, so this Laplace transform, the capital F, Xi, is what we call the moment generating function. The moment generating function, and we can derive moments from this. We call these moments m with index a, b, and c. And what we do is we take derivatives with respect to xi, upsilon, and zeta of order. So the eighth derivative with xi, the b's derivative with upsilon, and the c's derivative within zeta of this function. And after taking the derivative, we evaluate this at the velocity frequency of 0. So this is, if you will, the development point. 0 is the development point. Yeah? 0 frequency is development point. the development point, because if you think a little bit harder about this, then you will find that these are the coefficients of a series expansion. Of f c at, xc equal to 0. So I always tell the bachelor students that everything in numerics starts with the Taylor series, yeah. And now, what does the Taylor series contain? It contains increasing derivatives of the function that you're trying to approximate, yeah. So then, the moments are basically, so since the moments are the derivatives of this function, they are actually the coefficients in the series, almost the coefficients in the Taylor series, because the Taylor series in addition has this 1 over n factorial in front. And so, but this is something that is basically known, as it would be constant, yeah. So this is taken out here. And otherwise, these are just now the coefficients. So if you write a polynomial in the moments, you basically get the f. Yeah? Okay, now we do a little bit of simplification. By the way, this is something that you will probably not find in the book like this. I always have to apologize that I did not read the book, so I'm not completely sure. But you will probably find where we are getting to. Yeah? So we do a simplification. Again, we say that our velocity has 3 components, xi, small upsilon and small zeta, and we apply our definition MABC with all these derivatives. I have to write a little bit now. Derivative B upsilon, so this is not the gamma, this is upsilon. C. So now, well, what is f? F is the integral, yeah? F is the integral over f of xi, e by the power of xi times the uppercase xi, all of this at xi equal to 0, and this integrated over xi. Okay, now what is important is that these derivatives here, they only act on the xi, on the capital Xi, and not on the small xi. So they don't, you see, they don't seem to act on the distribution function. So we can put this into the integral. What we see is we are taking in incremental integrals over the Euler function here, and you know what this is. This just gets out the exponent in front of it. So basically, this leads to this integral over f xi. Now, what comes out if you take the 8th derivative of e by the power of xi times capital Xi is this xi, so to do it a times, so you get out xi by the power of a, right? And you get upsilon by the power of b and zeta by the power of c, and then you get e again power xi, and this vector, and this equal to this equal to 0. So if you want to apply now, the only place where the xi still appears is in this exponent, yeah. And now you know that it is supposed to be executed at a frequency 0. So you put 0 into the exponent, and then you see that this will come out as 1. All of this together, such that what you end up with is from the integral from minus infinity to infinity of f xi multiplied with xi by the power of a upsilon by the power of b and etc. by the power of c dxc. So and if you look in potentially the book, and most, I mean, maybe some people think that it does not really matter where the stuff is coming from. But there are sometimes good reasons that you have to know where things are coming from. And we come to this not in this lecture, but in a later lecture. Yeah. So what you will often see claimed in literature, that this is the definition of moments. Yeah. So this is the simplification that you arrive at if you apply all of this. And usually, if you look in literature, so they would say this has been done 100 years ago. We just start from this, which a little bit causes the problem that we have now generations of students that do not actually know where the stuff originally came from, because they all think that it started like here, yeah, but it comes from the moment generating function and these derivatives, and this actually has some significance if you want to change what you are actually doing. And one of the things that we want to change is the frame of reference. So there's something, and this we come to into 10 minutes or so. Okay, so the thing that we call these things that come out here, we call them countable raw moments. What we mean by this is that we can count them, A, B, and C. So we can count A, B, and C from 0 to infinity, right? So this is, by the way, this is vector counting. It's not one-dimensional counting, yeah? Because we count A, B, and C separately, yeah? But we can count them, not in 1D, but in many dimensions. So, and raw, we mean the lab frame. So if you don't take anything from this lecture here, so you can, other than you can tell your children, yeah, so I learned that I can, how to count in multi-dimensions. Oops, we lost our guest here. Yeah. So, raw countable moments. Moments can, of course, be defined in different ways now. According to their frame of reference. We can specify orthogonality conditions, and we can specify normalizations. So normalizations just mean we scale the entire thing, yeah, with a constant, yeah. And okay, so the first and one of the most important things here is the frame of reference. Frame of how are we doing in time? Or roughly, okay. So frame of reference. There are infinitely many frames of reference, but the two that we are always talking about is the Eulerian and the Lagrangian. So we have Eulerian and Lagrangian. So these are the two we are always talking about. The Eulerian is the laboratory frame. What am I writing? Laboratory frame. So, which means there is a stationary observer. And the Lagrangian is the material frame. This is the frame that is moving with the object we are describing. In this case, because we are doing fluid dynamics, is the flow. Yeah, we are moving with the flow. Okay, so Euler is standing on the shore and Lagrange is in the boat. Yeah, that's the thing. So if we take moments in the Eulerian frame, as we just did, we call this thing raw moments. If we if we take moments in the Lagrangian frame, we call them central moments. But there is a non-zero possibility that you also find other names referring to them in some place in the literature. Yeah? So, but we call them central and raw moments. The difference can be used in a Galilean transformation. Cannot write Galilean. Galilean transformation. So let's think this through this way. Say we have here Xi, and we have here our F. And now we have our say something that's similar to an equilibrium distribution function, which means that most of the velocities have very, very small probability, yeah, and only a certain velocity has a high probability, and this, together with due to the temperature, has a certain width, yeah. So we've seen this must be a Gauss function, so it would usually look something like this, okay, and this will be centered. This is why we call this central moment. So in here, this Xi is equal to 0 in the lab frame. And the center of this velocity is at the velocity of the object or the gas, the liquid, yeah, velocity u. And now the difference is if this here is F, so the distribution, the population in the frame, in the laboratory frame, then we can also write the population in the moving frame, and we could call this, for example, F with this, with its snake, tilde, I don't know, with respect to the velocity u. Yeah, so now we can shift the entire distribution. The one is in the laboratory frame and the other one is in the moving frame. Yeah? So we can then say that f u with this thing on the top of xi is f of xi plus u. This is the a Galilean transformation. Yeah, just to shift something by a velocity. What does this mean for the moments? So look at the moments. We have our, you know, for doing math is always important to know where stuff is coming from. Yeah. So if you always start from where you already have included all the simplifications, and now you want to change something, then you always have to think, would it have been necessary to do this before we did the simplification? Yeah. Yeah. So if you know where things are coming from, then you always know what you are allowed to do and what you are not allowed to do. Now let's look at our definition here. So see, we want to get f of our new so the moments of this shifted Galilean transformed distribution, then we can say, so this is obviously the same as this here, yeah, e by the power of xi times the other xi, the xi. Okay, so since everything in this integral goes from minus infinity to infinity, we can shift the entire integral by the velocity without changing anything. Yeah, so we can just replace this here with f of xi. So we can put this up here, and now we have to change this. So yeah, so we shift this by u, the entire thing by u, and nothing has changed because the integral, yeah, so if you say it is now going from minus infinity plus or minus u until infinity plus u, yeah? No, it would be in both directions the same, yeah? But anyway, so this would not change here. So we put this, now we put this up here, and now if you go through the procedure that we had before, what you'll end up is that as you see here, we take the derivative of the capital Xi, so and everything that is in front of it comes down, yeah, in the definition of the moment. So this leads us to the central moment, central countable moments. Which in this lecture here we'll write with K, KABC. KABC is the integral, so of xi, f over xi, and now instead of having here xi by the power of u, we get xi minus u by the power of a, upsilon minus uy by the power of b, and zeta minus uz by the power of c, and this integrated over xi. Now, we declare by definition of saying the moment is central. So if you go into the moving frame, what is the velocity that you measure if you are in the moving frame? What is 0, right? So then we define that k 100 is the momentum, yeah, first moment in the direction x. So we define that this here is 0, we define that this here is 0, and we define that k001 is 0. So from this, arises, let me see, from this arises that, okay, so from this you can actually calculate what is ux, what is uy, and what is uz, and this is exactly the velocity in which your frame is moving. Yeah? I was in the impression that I wanted to derive this, but no, I don't. I want to do something else. I want to state that there's one quantity that is, as we say, Galilean invariant. This is the density. Yeah, so obviously, if you put A, B, and C to 0, everything vanishes here, means that and you only integrate over F, means that it does not matter in which frame you measure the density, it will always be the same, which means that M00 is equal to K000. So the zero moment is automatically always the same. And this is we call zero moment. And I've not introduced so far the order of the moments. This is something that we'll use a lot. The order of a moment is just the sum of its indices. So, for example, there will be 6 second order moments. So, the sum of the index must be 2. So the easiest way is first index is 2 and the others are 0, right? So you see then there is a 0 to 0, also sum is 2, 0, 0, 2. So these are 3 moments, and obviously then comes M110, M101, and M011. Right? So there is exactly six moments of order 2. Now I believe last time we've already talked about the second order moment being related to energy and temperature. Let's look at the temperature. The temperature in raw moments. So T. Okay, so there is a prefactor that of course comes from physics. So there's the mass of the particle 3 times the density rho times the Boltzmann constant. Yeah, so this is transforming, and the integral, I mean the energy that comes out, yeah, into temperature, because temperature is an invention that has been there long before we know what energy is, and long before we know that this means that there's particles flying around. So then somehow we have to have a prefactor that defines us when we actually measure the movements of the particles, what does this actually mean in Kelvin? Yeah? So this is why we have this prefactor. We don't need to care about this. And then we get, so we get the distribution function. And the kernel over which we have to integrate in order to get this as a moment is xi minus the velocity. Yeah, so it's very important. We have to subtract the velocity here because we consider the macroscopic kinetic energy of a body not to be part of its energy. Yeah? So unless it is so small that we do not recognize it as a body itself and everything around it moves in a different direction, then suddenly the kinetic energy becomes thermal energy. Yeah. So what is thermal energy and what is kinetic energy is the question of scale. Yeah. And of course, that there's a statistical distribution of this. So, and then we have to integrate this over xi. So, if we want to do this, this actually looks like this. There's this prefactor M3 rho Boltzmann integral. So we write this thing out. So this is xi times xi minus 2u xi. So this is binomische Formel. What is this in English? Binomial equation, I guess. Yeah. And this can be further expanded in everything. So this has all its components. So xi dot xi is of course the components xi square plus upsilon square plus zeta square and u times, there needs to be a scalar product, of course, right? So this gets into minus 2u x. So, and now comes here the first moment, m00, minus 2uy m01. So because, I mean, we do the integral over xi, yeah? So here, you see, I missed, sorry. I missed the line, sorry. I was one step ahead of what I wanted to write, sorry, I'm very sorry. So we multiply this by xi minus u y u minus 2u zeta plus u squared plus uy plus uz squared. So because I just noticed I missed the point that I actually wanted to explain. Yeah? Now I've distributed everything out. Why did I do this? Now obviously, when we integrate over a sum, we can put this as a sum of integrals, right? And this integral, the sum of integrals will give us different moments. And you see here we have f times xi square. So if we take this out, this will give us the first moment. Yeah. Let me just write M3 rho K Boltzmann. So this will give us the second moment in x direction, which is M200. Yeah? Yeah, because we integrated only f times this. Now we integrate only f times this, and now we get plus M0 0, and then we integrate only f times this and get m002. So, okay, so far so simple. Now what happens here? We have here minus 2u xi. And as far as the integral goes, ux is of course a constant here. So you can take this out. So what you end up with is an integral f xi times xi, which we know is a first moment. Yeah? So we get this minus 2ux, we can take this in front and then end up with the first moment, and this is the first moment in x. So it's m10100, and the same thing will happen for the next guy too. So minus 2uy is a constant, and then we end up only with the integral over epsilon times f, yeah, which is the first moment in the first moment in the x direction, and then with the theta, we of course do this fit this here, minus 2u z m001. And now we have this stuff left, which is all constant. Yeah? So if we integrate only over f, we get the zero order moment. So what we end up with is we get all of these times the zero order moment. So, and now we have to identify what this is. So m100 is the momentum. So it's the density times the velocity. And this will cause this here obviously to be ux squared times rho. Yeah? The same thing with this guy, uy squared times rho, and so 2 times. Yeah. No, sorry. You always have to watch out where you put your brackets to. So this will be u z rho, okay? Which means, so yeah, and this thing here is rho. I have the feeling I have to speed up a little. M00 is rho. M100 is rho times ux. M010 is rho times uy. And M001 is equal to rho times uz. Which means if we collect all of this, okay, I'll say the following. So we have here ux squared, and we have here minus 2ux squared. Yeah? So this will cancel out with one of these. Yeah? So that in the end we have t is equal to 3 rho k Boltzmann, and we end up with m200 plus m020 plus m002, and now minus only, we can combine this again to this vector u times rho. Yeah? So now what you can identify is that the temperature, yeah, is the second order moments minus the kinetic energy. The kinetic energy is u times u. Yeah? That's density. So, and obviously this also means that t in central moments, so in central moments the velocity is obviously disappearing, so t is m rho k Boltzmann, and this will be k200 plus k02 plus k002. Okay, 15 minutes. Any questions to this, or should we come to orthogonality? So if anything of this was confusing, I'm a very bad teacher. If anything of this was confusing, then I can top it. Was anything confusing?
I was just confused by yes, there was one thing which was confusing.
Okay.
So at the beginning, you mentioned that we were on the frequencies. So what I understood is that we're at frequencies, and when we change, or by the Laplace transform, we went to the momentum space.
No, moment space. Be careful what you say. Don't say momentum space, say moment space.
Okay, moment space. But then I was confused. So we're working with distributions. Then somehow it's like a probability to see something, or that you can see this velocity.
Yeah.
So instead of, so that's why we use the inverse. So it would be inverse Fourier transform, right?
I cannot answer you why we do it this way and not the other way around, other than saying that we prefer to deal with positive energies.
Okay.
Yeah. So this is a convention. There is no higher meaning behind using the forward or the backward transform.
Okay.
Yeah. Okay. Let's try out the following here. I say orthogonality and the quest for independence. There is something that actually confuses not only students but everybody who is working with the thing, and the important thing to understand is that it is confusing. If you believe it was not confusing, then you misunderstand the topic. Okay? So because there are a lot of people around that believe it is not confusing, and they are all wrong. So orthogonality in the quest for independence. So what we would like to have is, if we make our moment expansion, that each moment gives us different information from all the other moments. Right? Yeah, so we are the first thing we are starting as a startup question is whether this is actually true for the equilibrium. So let's look at the equilibrium, and now I write the stuff down without actually introducing it. So as I said before, we just had the structure. The actual distribution then looks strange. So this, or like this. So this is the thing that we have in front of this. This was our factor R. Then we have a minus. We have minus xi times an m, and this divided by 2 Boltzmann t. So this is, you see, this is already in the center of mass frame, yeah, because there is no velocity other than no velocity in it, yeah. So this would give us the equilibrium, and this would describe in gas at rest. So it's not entirely important, these terms. This is just the way they look like. So if we get second order moments out of this, or this particular second order moment, m200 of this equilibrium, we of course take the integral over the entire thing by the power of 2/3 e minus xi times xi m to okay, Boltzmann T, and we multiply this with xi times xi. Okay, not vector, because we are only looking at 2. Yeah, the other one would be the sum of them, right? So 2, 0, 0. So this is why it's not vector, it's xi square. Clear why? Is it clear why?
Yes.
Yeah, okay. So, and then we integrate this over xi. And I've used Mathematica for doing this. Yeah, because you can do this. It's a bit difficult to do it by hand. So what Mathematica came up with is rho k Boltzmann T divided by m. And then look at another moment, the first order moment, rho 2 pi k b t by m 2/3 IME minus xi times m2. So in order to get the fourth moment, we have to multiply with xi by the power of 4. Again, this is without vector. And I let Mathematica do this, and what comes out is 3 rho k Boltzmann T divided by m, and this is square. So what we basically get with the first order moment is we get the temperature squared. And this could be understood as kind of a little bit disappointing, because the other moment does not give us any more information. Yeah, I mean, this is of course the case because we are looking at equilibrium, where no more information actually is in the system. But suppose we are not in equilibrium, then also we have the case that in the first order moments, the first order moment obviously depends on the second order moment. Yeah, and so if we look for any new information in this other moment, we first have to get rid somehow of the temperature. Yeah, and let me just briefly write this down. M200 and M400 carry the same information in equilibrium. And now the thing that we wanted, that we would like to do, is to actually find variables that are independent of each other. So it's necessary, or just at least preferable, to make variables independent of each other. So, and one way this is usually attempted to be done is by orthogonalization. I write attempted because these attempts often fail if not done correctly. Okay, we need the definition, and I noticed that I will take some overtime, but I have to remind you that officially this would be a 3-hour course, yeah, where we had so I have a better feeling. It is counting this as 3 hours when I take a little bit longer than 2 hours, because I have to, tell the university that I'm actually doing enough teaching. So let's define a moment M as an integral from -infinity to infinity over a function, over a distribution f with a kernel M, which this kernel can depend on xi, and we integrate this thing over xi. So this is one moment, yeah? And then there is a moment n that is a similar integral, just with a different kernel. That is phi n of xi. Okay, so this is given. And now we say that these moments with these kernels are orthogonal with each other when they follow the following. So moments with kernels phi m and phi n are called orthogonal with weights W of xi if the following condition is true, that the integral from -infinity to infinity, given the weight over phi m and phi n, all of this integrated is equal to 0. If this is the case, then there is orthogonality with weight W. And this is very important, because this kind of orthogonality only holds together with this weight. So if you change the weight, the orthogonality condition is different. Yeah? So it's very important to know what is this weight. I mean, you can set the weight to 1, but then you actually in practice you are doing something wrong then. Okay, so the reason why this is often done in practice, in particular in the lattice Boltzmann methods, is that we wanted to have these two things when they are orthogonal. Then they are supposed to carry independent information. And the problem here is that what we mean by independent is not well mathematically defined, such that this becomes a very fuzzy discussion in some cases. Yeah. So I'm telling you all of this. Yeah. Just when you come across somebody who is very convinced that they understand this, and tell you something, so be careful. Yeah, so there's some true things and some false things here that can come. We'll go through these things in later lectures. One application here is with that is one of the better choices is to use the so-called Hermite polynomials. So the Hermite polynomials have the idea that we attempt to make them orthogonal in the equilibrium. Orthogonal at equilibrium. So the idea here is that the weight function is the equilibrium. So with this, you can separate information in distributions that are in equilibrium. Yeah? Problem is, when you are already in equilibrium, you already know what information there actually is. So basically, the assumption is if your distribution is almost in equilibrium, then these things are almost independent, yeah, but not completely, yeah. But so this is done by, how is it done? We assume the equilibrium, of course, of the form is proportional to be of the form. So this is now an x. Okay, Hermite polynomials are, of course, given for general functions. There's nothing necessarily to do with the Boltzmann method. So if we have an equilibrium in x, then we have minus e minus x by the power of minus x square divided by a standard deviation squared. So sigma is a standard deviation. So would we in physics be related to the temperature? And x is the random variable, so this would be, in our case, the velocity. So now the kernels for this, now the kernels for these moments, phi n, of x and x divided by sigma. So we normalize this, x by x divided by sigma, can be computed. So I hope this is everything correct, because I wrote it from somewhere. I don't know this by heart. So it's minus x by the power of n, and then e by the power of x squared by sigma squared, and then we take the nth derivative of e by the power of minus x square sigma square, and this thing here. So if you take these derivatives, so you get the e function, and they will cancel out with this one, and you actually get a polynomial, and these are called the Hermite polynomials. Of degree n. So the zero order Hermite polynomial is 1. The first order Hermite polynomial is 2x divided by sigma, and the second order polynomial is minus 2 plus 4x squared by sigma square. So important, when we compute our usual raw moments, we integrate over monomials, right? Only xc square, xc by the power of 3 or so, in order to get these things orthogonal by the definition of Hermite. The kernel functions are no longer monomials, but actually polynomials. They come up with different orders in x here, yeah? And they become, of course, more complicated if you go to higher orders. But the one thing that is important in the Lattice-Boltzmann method is that we have many dimensions, and therefore we look at the multidimensional Hermite polynomials. and they are generated by factorization. So we say that the entire function, so phi, n, m, l. So now they have 3 dimensions, yeah? And these dimensions are supposed to be in xi divided by sigma, upsilon divided by sigma, and zeta divided by sigma, where sigma now would be related to the temperature, yeah? Is then the product of phi of the one-dimensional Hermite polynomials. So we get multi-dimensional Hermite polynomials by multiplying one-dimensional Hermite polynomials. Phi L zeta divided by sigma. And this can also be changed to central Hermite polynomials where I again use this tilde NML of xi by sigma, upsilon by sigma, and zeta by sigma. So we get these guys by just doing the Galilean transformation. We subtract ux from xi. We subtract, now this is upsilon, sorry. This is upsilon, we subtract uy from these, and from the last one we have zeta minus uz divided by sigma. So now we have to stop here because of time, and I hope few of these things will become clearer when we go further on next week. By the way, yeah, next week there is no reason why there should not be a lecture. Yeah, next week because it's Friday. Yeah, and so we'll have the lecture next week. Yeah, so if you use these kernels, you generate orthogonality at the equilibrium. Yeah, for now, in particular, if you use central moments, you will generate orthogonality of the distribution that has the velocity ux, uy, uz. Yeah. Important thing here is if you use the same thing for a distribution that has another velocity, then these things are not orthogonal to each other. So, and this problem that how independence between moments is actually obtained is something that we'll talk about in later lectures. So I'll going to stop the recording. Thank you for attending and listening.